So good afternoon, everybody, and thank you for joining us, and welcome to the Future of UVEB Advanced Manufacturing, Trends, Strategies, and Applications webinar being presented today by the International Ultraviolet Association, RadTech, and the State University of New York College of Environmental Science and Forestry. My name is Brandon Murphy. I'm your host today here at ESF. Just some quick logistics for today. We'll be having our speakers present, and then at the end of their presentation, we'll open up a Q&A window where you can type in questions, and our presenters will read and verbally answer your questions. Also, as a reminder, all webinars in the UVEB Advanced Manufacturing series are archived at esf.edu/openacademy/UVEB webinar. You'll also get a follow-up email automatically at the end, a little while after the webinar, with a reminder of that address, so don't worry about trying to write that down. We hope that you will consider joining us for some upcoming conferences around the issues and technologies being discussed today. And the 2019 IUVA World Congress is coming right up, February 10th through 13th in Sydney, Australia. Please visit iuva.org for more info and to register. And also, the RadTech Big Ideas Conference is coming up March 19th through 20th in Redondo Beach, California. Please visit the bigideasconference.com or radtech.org for more information on that and to register. So today's webinar, New UV-Based Interventions to Enhance the Food Safety of Fresh Produce, is going to be presented by two speakers. Dr. Keith Warriner is a professor of the Department of Food Science at the University of Guelph, and Dr. Tatiana Koutchma is a research scientist at the Department of Agriculture and Agrifood, Canada. Dr. Warriner will be starting us off today.
Oh, thanks for the introduction. So thanks everyone for joining the webinar today. And what we'll be talking about is the #1 cause of foodborne illness outbreaks, and that's fresh produce. So fresh produce foodborne illness outbreaks has been around for many years, and the reality is that we've got quite a good understanding of the roots of contamination in terms of in the field environment. But what we haven't really got a handle on yet is interventions at post-harvest. The reality is that we depend on post-harvest washing, and we've known for about 5 years now that there's more risk of cross-contamination and decontamination. So what I'm hoping to do in this sort of introductory part of it is really introduce the nature of the food safety issue, and also some of the barriers of why haven't people got better interventions for decontaminating produce. So to put a sort of perspective on it, the ready-to-eat salads market, or bag salads if you want to call them that, is rapidly growing. It still grows around about 10% a year, multi-billion-dollar industry, global industry when we think about it. And over the years, we've got this centralization. So, for example, 80% of the leafy greens that enter Canada are actually derived from Arizona and California. And when we look around to other produce types, we can see these centralized productions, be it tomatoes in Florida, etc. Now, the reality is that even though it's a very big market, the margins are always low because the retailers squeeze the profit margins. And when you think about logistics and distribution and things like that, it adds to the cost. So what you'll find if you enter the fresh produce market is that you've got to show clear benefit of a technology. So you might come in with food safety in mind, but basically food safety is something that happens to someone else. These outbreaks are always going to happen to other people, not me. So the best way to approach the market is to add added value. I can give you extra shelf life. I can I can enhance the quality of your product. And that's the kind of approach I have to take in the fresh produce sector. Now, as a historical perspective, certainly fresh produce, as we said, from the first time lettuce was grown, I'm pretty sure there was a foodborne illness outbreak, because it's very prone to contamination. As is other fresh produce, it's an open field, a very open system, without any effective post-harvest interventions, apart from irradiation, which nobody wants. So when you look back in the history, there was a big spike in about 95 about foodborne illness outbreaks are linked to fresh produce. And this coincided with two events. One event being the bagged lettuce, the pre-prepared lettuce and other bagged salads that was coming through. And the other thing was this introduction of hydrocooling, vacuum cooling, which basically draws bacteria and pathogens into the internal tissue. So when you start processing something, or when you start cooling under vacuum, you're going to be at greater risk of pathogens that are going to transfer, spread, and hence we've got this big increase. And obviously you can say, well, the volume of the market increased and also our ability to detect, which is very true. Now, what you would do when you're looking at interventions is say, well, what's the biggest problems at the moment? And by far none, sprouted seeds are responsible for most foodborne illness outbreaks, but sprouted seeds are a different category to fresh produce, like mung beans, alfalfa, for the simple reason most of the time the contamination is on the seed, and when you sprout it to make sprouts, you basically propagate, enrich the pathogen. But we'll look at the other list. Leafy greens, been involved in over 38, well, more than that, outbreaks of foodborne illness, tomatoes, which has a better history recently, but things like melon, soft fruit. So these are the targets. These are the ones that we're most interested in, what you really should be targeting if you're going to food safety interventions. And all you have to do is look at the news and you see a whole range of different outbreaks going on. So who could forget, for example, the one with Dole a few years ago in their Ohio plant, where they got the listeria, endemic listeria population, and it contaminated a whole range of different produce. And they also be able to DNA type that listeria and could actually trace it back to much earlier outbreaks and cases. So there's nowhere to hide in terms of saying, well, hopefully we won't detect it. With the diagnostics available now, they can fingerprint, type it, and get source attribution more than ever before. And we've got soft fruit with hepatitis, norovirus, cyclospora. And an interesting one that kind of went right under the radar when the romaine lettuce outbreaks were going on is with cucumbers. There was 3 outbreaks 2 years ago, and up here in Canada there was 2 outbreaks just recently, and even papaya. So the kind of produce contaminated is broad, and as you see these days, the source attribution is so good that so there's nowhere to hide, and hence they make the media more, and when it hits the media, it hits the market. But really, when we think about outbreaks, we can't help but notice about the romaine lettuce. So I'll go briefly through the romaine lettuce outbreaks. The first one happened in November 2017, and it's not the first time romaine lettuce have been implicated. You can go back to the 2012 or 2010, 2005 outbreak, and they were actually much bigger than this one. But they just went under the radar. In a lot of ways, this outbreak kind of went under the radar a little bit. It didn't get that much media attention because what happened, it was centered more in Canada in terms of outbreaks, and the public health came out saying, well, it's a health advisory, probably gone now. I wouldn't advise to eat lettuce, but no big deal. And the US didn't really, they followed up a little bit, but they didn't investigate it. Because what they hope to do is that when they do get outbreaks like this, they just want them to go into history and everything carries on as normal. But then something happened a few months later in that we got yet another outbreak. This was found in March 2018. And this is where most cases did happen in the US. And obviously, coming on the back of the other outbreak, they had to do something. So they got their traceability systems in place. And really what broke this case, or cracked the case, not broke it, is a contaminated batch of lettuce going up to Alaska. And obviously, once you've got a contained environment, so to speak, as a prison is, you can say, where did this lettuce come from? Oh, Arizona. So they went down to Arizona. They managed to piece the sort of elaborate tapestry together. And it is challenging because when you look at the distribution chain for fresh produce, what you have is many growers. And some of these growers are subcontracted and sub-subcontracted. And so what you get to the point of is the traceability is very difficult, especially given the traceability systems are fairly rudimentary. So once they're harvested by again, subcontractors, they usually go to a central processing plant. And this is why processing plants are such good intervention points, because you can see everything channels into it and everything gets distributed out of it. So through a bit of investigative efforts, they managed to actually find the farm. And the farm was in Arizona. Now, in a lot of cases, contamination is acquired in the field environment. It's very open. And for some odd reason, a lot of these produce fields are just downstream, or upstream, well no, downstream should I say, from feedlot farms. So with cattle, they harbour E. coli 157. They show no symptoms, so you can't identify which cattle are carrying, but they shed E. coli 157. And it gets into the canals, and sure enough, it goes down the canal into and gets used for irrigation water. And on this particular case, which is very common in outbreaks with leafy greens, it was in the latter part of the season, and also they had a sudden frost a few days before, which they said damaged the romaine lettuce so the E. coli could penetrate. But once it's inside, it grows very well. So the classic scenario is that irrigation invariably is the source of contamination. It's spread everywhere. And invariably, a feedlot farm or a farm of some nature is downstream, or upstream, I keep getting that wrong, upstream from the place where you can see the connection. Manure runoff into irrigation water, onto crops. There's nothing that can stop that being decontaminated. Washing or redistribute it rather than control it. So after 2 outbreaks in a row, the industry was suffering. So there was a program by Dr. Oz called the Salad Summit, and it made me laugh because I had all these big wigs from industry. I won't say the names because I don't want to. I hope they're not listening. Came out saying, look, we put regulatory things in place. It can't happen again. This was just a one-off. And any time you put yourself up, you're always going to be put into the spotlight. And sure enough, a few months later, which we've just seen, is that we got yet another outbreak. Now, interestingly, it followed the same kind of geographics as the previous outbreak in 2017, but more importantly, it was the same strain of E. coli. So that same strain of E. coli had either survived in the field, been deposited in the field, a continuous source of contamination. And when you get this third outbreak in a row, that really shattered the industry, because retailers were getting public health warnings saying, oh, you shouldn't eat romaine lettuce. The FDA did actually go one step more and recall it, but you couldn't get a blade of romaine lettuce. It was devastating economically, because one store, for example, lost $120,000. That's one store. And because it's an advisory, you don't get recall insurance. So it was a tough pill to take, that one. But certainly the FDA did come back saying, yes, we are going to recall it. So in the US, we're a bit more better off than we are in Canada. But as you can tell, it devastated the market. I was just at the supermarket last week, and romaine was on sale. They're trying to sell it as cheaply as possible. So they actually did get their act together this time. I managed to trace it back to the Adam Brothers farm. And it's interesting when you hear about the Adam Brothers saying, oh, 5th generation, the good people, they don't produce tainted crops. It doesn't matter if you're good or bad. If E. coli gets in the system, it's going to get onto your crop. It's going to make people ill. So this was traced back to California, probably the same one in 2017. And hopefully that spurs the industry into action. Now, the trouble with the industry is that it denials. It's still in denial in a lot of ways, in that there was this perishable pundit who comes out with this article in the Wall Street Journal saying, well, when you think about it, a small number of people get ill. Percentage-wise, it's very small. But what they seem to not realize is that if you're one of those people that get ill, you could possibly die from it. And you get all these stories now where people get ill, they die, usually the elderly and the young. And also, obviously, if you do survive, you can have kidney dialysis, you might be paralyzed. So this perishable pundit by the industry, but this is what the industry is. It comes out with sound bites. The leafy greens marketing agreement comes out with saying to the FDA, saying, oh, thank you for the investigation. I know we should have known this to start with, but the reality is that they come out with statements saying, oh, we'll improve, we'll learn from this, but they never do. Everyone knows what the problem is. So thankfully, I think the industry is realizing, saying we need to change technologies. They talk about testing, which isn't going to be any use at all. They talk about traceability, which is fine if you want a staple door, but they want interventions. And in terms of interventions, I'm going to just focus on the UV ones, obviously. There are a whole plethora of them. A simple UV irrigation system, which they use in some countries to actually reduce spoilage of plant pathogens, could be easily adapted. The one thing California and Arizona have is a lot of sunshine. And even then, you've got systems that can decontaminate irrigation water. So the reality is that when you talk to farmers, they say, well, we've got so much irrigation water, we cannot possibly decontaminate it. And they always come back to the sort of fact saying, well, if in 1900s we said, well, we've supplied so much water to the population, we can't decontaminate it, I think we'll all be still dying of dysentery and things like that. But there is challenges in terms of treatment with irrigation water in that it's not pristine. You've got a canal and it can have high turbidity. And as you all know, turbidity blocks UV light. So you have to be a bit inventive in terms of what reactors to use. And there are mixing reactors, Dean flow reactor, telecurette reactors that can handle this sort of water. But you can't just put a UV lamp in and hope for the best, because the water, as I said, can be a bit turbid. You're looking at about NTUs of 60, which, as you can see, you can't even see through. So you have to be a bit challenging for that. But the reality is, as I mentioned earlier, is that you can try and prevent contamination in the field, but if the irrigation water doesn't get you, then wild animals can come in. You can have flood events. You can have manure amendments which are put into the soil because people like to have organic sort of farming. And all these carry a risk of pathogens. And these pathogens are the bad ones, the E.coli 157s that can cause kidney failure and death, Listeria monocytogenes. If you get listeriosis, 30% chance of dying. Salmonella, multi-drug resistant, norovirus, the winter flu, hepatitis, and more common these days is the parasites. These are the ones that give you persistent diarrhea, like Cyclospora and Cryptosporidium. So what the industry really needs is this firewall that separates processing from the field. And under the Modernisation Act, which was introduced a few years ago, they had the final produce rule, which specifically says you need to have a validated prevention control in processing and in the field environment as well. And so when you look at process controls, these are part of the food safety plan, but these are interventions. Yes, you certainly can depend on sanitation, GMP, and supply verification to say we're producing pathogen-free crops if you believe them, but you need it validating. So again, with the wash process, this has been very challenging because the reality is washing doesn't work. The best you can achieve with washing is to avoid cross-contamination. And there's been a lot of attempts to verify or get methods to verify and validate post-harvest washes, but there's none there that actually work. You can try and look at sanitizer concentration, but it's a moving ball. You can look at contact time and turbidity. But we all know that post-harvest washing at the moment is the best you can achieve is avoiding cross-contamination. You can't depend on it for decontamination, which isn't good. So we move on to UV. What could UV offer? Well, certainly you can get UV tunnels, and depending on the kind of produce you have, is fairly effective. But as you could imagine, when you think about the surface of fresh produce, not all can be directly UV treated for the simple fact that you get shading areas and things like that. So direct UV treatment is problematic for the simple reason of the shading effects. And this is well illustrated in this UV treatment of apricots. Yeah, you get a certain log reduction, but then you get this tailing effect. And the tailing effect isn't due to this hyper-resistant pathogen present, but it's actually down to shading. The UV has to contact the pathogen in order for it to work. So in this example, this just illustrates it even more in that even on a sound surface, you can get things called trichomes, which are hairs that can protect the actual pathogens. So if you get damaged areas, you get shading because you've got nice crevices, and even in spoiled products, which shouldn't really be consumed. But the reality is you get these shading effects as well. And so the net result is that you get a decrease, but you can't get removal, which is the big challenge, isn't it? Now, what you can do to increase the UV target area or the UV illumination area is use these drum-type reactors. So as the name suggests, these are tumblers that rotate the produce, and hopefully you'll contact them. I've seen prototypes. I've never seen the results from them, so I assume they're not that effective, and they probably do more damage to the produce than anything else. So tumble reactors are available. I've never heard anything substantial about them in terms of do they work or don't they work, but you could see they're good for certain products, but I think the mechanical damage will be too much. And so you might think, well, let's really blast it with UV, but you've got to be careful at blasting with UV, because even though UV isn't damaging at low doses, it can be damaging at high doses. It can cause discoloration through activation of the polyphenol oxidase. It can cause, obviously, drying effects, which isn't good because that increases the prone to damage, and you can get actual degradation of the plant material itself if it's very overexposed. So you're kind of limited to the UV dose, and obviously it varies significantly between produce types. But certainly when we think about apples, for example, we think about furans and other products, and these furans are carcinogenic, so you can't really just blast it with UV and hope that you'll reach the target. So what we did in our research is use something called an Advanced Oxidative Process. So in the Advanced Oxidative Process, you actually generate free radicals, hydroxy radicals, which essentially can be produced by the UV degradation of hydrogen peroxide or ozone, or a combination of the two, or the combination of the three. So if you like, you're producing hydroxy radicals in order to de-inactivate the pathogens, and you get away from the shading effect. So this was our Mark I years ago, a simple spray head with a peroxide and a UV lamp. It worked quite well, and we went to the Mark II, which was more a sort of batch system with a UV where we introduced a spray of peroxide. Both have the same effect. You're putting peroxide into a system and inactivating the pathogens, both on the surface and subsurface. And this was some of the results we got from years ago. And the hypo is hypochlorite washing, basically post-harvest washing, which you can see does very little to the salmonella in this case. We did do it with E.coli as well. So the hypochlorite washing doesn't do anything internal, bit external. But when we use the AOP system, you got very high external counts. So on iceberg lettuce, for example, up to a 4-log reduction. And even on the subsurface, the stomata, cut edges, you can get that penetration. So based on these results, it was scaled up to Mark III. So this is the Mark III one, which was a continuous process rather than a batch process. And through this system, we got the same kind of thing. We introduced the peroxide as a vapor, as a fog. And we were getting, and this was just a one treatment, a 3% peroxide and 30-second treatment. And you can see the cantaloupes were fairly easy to decontaminate. Zucchinis and tomatoes surprisingly were harder, but we can further sort of optimize that. But it's fairly versatile. Cucumbers, you've got a good log reduction compared to what you would be washing with. And this actually has gone up further in terms of looking at decontamination of leafy greens. And what we use for this is kind of a hurdle attempt. So what we have also is a technology based on forced air ozone, where we can treat the lettuce to remove the contamination from the outside, which is where most of the contamination obviously resides, given the nature of the contamination sources. Then it was put through a sort of chlorine dioxide wash, because you always have to use water in lettuce production for the simple reason it sticks everywhere, you can't transport it. And then we did the advanced oxidative process at the end. And long story short, we've got a 4-log reduction using that hurdle approach. So you can see we're not using UV on its own. We're actually using it as a supporting tool in combination with different hurdles to get the desired effect of pathogen-free lettuce. Now, this technology is being commercialized. This one here is actually used on apples. It's a very small unit, but this one here was just recently installed in California. It's 30 foot long, and it can do about 3,000 lemons an hour. So you can see how scalability it is, and people are buying into it for the simple reason it's an more effective method than washing, doesn't change the quality of the produce, and it's just one of those applications of UV that some people might not have appreciated. So in terms of advanced oxidative process, it's not just useful for fresh produce. It could be used for the crates because the crates have been identified as a source of cross-contamination due to the difficulty in decontaminating them. And really what we're doing is looking at other sort of produce types and also using the AOP process to actually improve the post-harvest wash. And we do that by sequestering these constituents that can react with chlorine, so it's easier to maintain the chlorine levels than the meats we're decontaminating as well. So as I mentioned to you, you can bring the best technologies to the industry, but there's barriers to overcome. Certainly in the fresh produce industry, is this barrier about we don't do anything new. We've done it all the time and we're going to do it. Certainly when you look at the outbreaks, people say, well, we get an outbreak every now and again, but it's never going to happen to us. It's going to die down and we'll go back to normal. But you can see by the number of outbreaks and recalls, was just one this morning, they're starting to tap up very frequently, so the industry has to do something. And as I mentioned to you, you've got to prove added value. So if we went in with shelf life extension, which some of the people who use the technology actually are more interested in, that's a much better way into the market. And there is a reluctance to change. And as I say, they're just going to get over this denial, and then they should be good to go. So with that, I'd like to now hand it over to Tatiana, who will present her research on using LED UV.
Good afternoon, everybody. I hope that you can hear me well. My voice may sound, not very good because I had a cold recently. So my second part of this webinar, will focus on the research that we conducted with my group in Agriculture and Agrifood Canada. And we were focused on testing feasibility of UV-based intervention to inactivate pathogens on fresh produce using UV LEDs. And also we tested water-assisted processing. So in my presentation, after short introduction into UV LED technology and possible applications of LEDs in food production, I will discuss the results that we received in our lab in testing effect of multiple UV wavelengths of LED on food-related pathogens, and the results of the next step of our research of effects of UV treatment on fresh produce using dry and water-assisted treatments. So as Keith mentioned, there is with an increased rate of with increased demand for fresh produce, there is also increased rate of outbreaks, and this dictates very important need for new antimicrobial interventions. So, and UV can be one of the technologies that can be right for improved safety of fresh produce because of its unique advantages, such as the UV is a purely non-thermal method, non-ionizing, non-chemical, and in food facilities and food production, it can be used for both, for prevention of cross-contamination in the facility itself, and to be a hurdle, or to be used individually, or to be used as a hurdle when combined with other methods. So talking about UV light, for many years we were mainly focused on germicidal action of UVC. part of UV spectrum that actually covers electromagnetic spectrum from 100 to 400 nanometers, because UVC between 100 and 200 nanometers directly damage DNA. However, we are kind of, less focused on bactericidal actions of UVA and UVB parts that also have can damage DNA, but due to different mechanisms, and can be very supplemental to UVC. So, and actually, one of the advantages of UV LEDs that they offer us this possibility to use, the whole spectrum of UV. So, because right now the situation is that in food industry we are using only two mercury lamps, only two types of mercury lamps: low pressure mercury lamps for treating food itself, and medium pressure lamps that are typically used for water disinfection. And one of the disadvantages of this lamp is that UV low pressure mercury lamp has very narrow monochromatic spectrum, and if compare with DNA absorption spectrum of E.coli, for example, we can see that actually it doesn't match to the maximum absorbers of DNA of E.coli. So talking about about the advantages of UV LEDs for food production, yes, the first thing I already mentioned, that yes, they can offer us multiple wavelengths and the benefit of their combination. The mechanism of action of a low pressure mercury lamp versus UV LED is very different. Ionization of mercury vapor versus excitation of electrons and semiconductive materials. The life, and of course, it's very hard to compare right now the lifetime of lamps versus LEDs. As far as I know, the maximum lifetime for lamps right now about 16,000 hours, maybe 18. And maximum lifetime for LEDs we can achieve for UV LEDs. We can achieve it's about 5,000 hours. And however, the UV LEDs, they are so small size, they can operate at cold temperatures. They don't have no toxic components like mercury. But right now, like I mentioned about their short lifetime and low power, of course, compared to UV lamps, and the cost is, still high. So talking about the range of application of LED in production and safety applications, of course, we should separate visible LEDs versus UV LEDs. So visible LEDs, they are very broadly used right now in horticulture production, crop production, and on farm scale, and for hydroponic farming, for urban vertical farms. They also can be used for enhancement of nutritional content and ripening control. And the reason for this is because the efficiency of visible LED is very high. It can reach, up to 80–90%, and their lifetime is up to 100,000 hours. So this technology, it's well established in crop production. UV LEDs, this is only emerging technology, and yes, with lifetime only up to 5,000, and yeah, the efficiency of LEDs, the maximum can be reached right now. It's up to 10 degrees, 10%. So, but talking about potential applications of UVA, UVB, and UVC LEDs, we can see that UVA can enhance the nutritional contents of fruit and vegetables. They can serve for spoilage control. Same for UVB and UVC. They can be used in broader spectrum for disinfection of food contact surfaces, packaging, fresh produce, and air, and can be very useful in point of use applications. So when we started our research with UV LEDs, I must say that the research on LEDs, for food, is very limited right now. So we have our hypothesis was that there are wavelengths that are more effective than 254, and they can be used for foodborne pathogens selectively. So, and this actual information exists for waterborne pathogens, but it's very limited for foodborne pathogens. And also we saw that, the combination of various wavelengths, this advantage of an ability to combine different wavelengths, UVA, UVB, and UVC may yield synergistic little effect. And using, lower power, we can achieve, high bactericidal efficiency. And also, because of the shading effects of UV light when it's used, directly for the surface disinfection, or we call it dry, treatment, we decided to test, the combination UV with water. So it means that, we combine inactivation by UV and removal by water. And there is actually industrial process that is used by Fresh Appeal company. They have commercial unit for this, this technology. But we wanted to test it on fresh produce and to see, okay, what kind of benefits we can get if we will do the exposure of fresh produce in water. So, so the first part of our research was focused on actually assessing germicidal efficacy of multiple wavelengths LEDs against food pathogens. And we worked with the common food pathogens that Keith just mentioned, such as E.coli, Listeria monocytogenes, and Salmonella pathogenic strains. And like I said, we looked at combined effect of multiple wavelengths, and the objective was to select an optimal wavelength for an activation of bacteria, not in model system, but on fresh produce itself. So in this first part of our research, we compared the UV light, monochromatic UV light at 254 from single low pressure lamp, and with light emitted at different wavelengths. And we had actually initially we had 4 wavelengths using Aquasense collimated beam unit. And because of we couldn't get to 75 nanometer wavelengths, we also used the chamber that was given us by Fusion, and we used this equipment for the research as well. So, and the first thing that we did, we built so-called germicidal action spectrum, and this is a plot of UV sensitivity of one organism, or versus the range of wavelengths. And as I mentioned already, this germicidal action spectrum, they exist for waterborne pathogens, because medium pressure broad spectrum lamps are often used in water treatment. But for foodborne pathogens, this data, they almost don't exist. So, like I said, 254 is the only approved wavelength for disinfection in food production. So, and this is our first result, actually. This is germicidal action for 3 pathogens that we chose, and for their non-pathogenic counterpart. And actually, our hypothesis was correct, that 254 nanometers was not the most effective wavelengths for disinfection. And you can see that, the peak in activation actually shifted, from 255 somewhere towards 268. 259, there was a maximum sensitivity for E.coli strains, and Listeria strains, for example, had the peak sensitivity at 268 nanometers. And later on, we saw this in our experiments, saw the difference in efficiency of these wavelengths when we conducted our experiments with the fresh produce directly. So also we saw there, not very typical response of some Salmonella strains that didn't correlate, directly with, DNA absorbance spectrum, that we relayed that, okay, there are also some different mechanisms, that can present when we are using LEDs. So this was very interesting, thing, and we are thinking about, to continue research in this area. And also the mechanism
Tatiana, we lost you there for a second.
Yeah, I know something happened. I've got a message that the session is over. I don't know why. So, anyways, I continue. So, also, in our research, we look at inactivation kinetics of E. coli. Can you hear me? Hello? Okay. Of inactivation of E. coli at different wavelengths. Okay. 254 versus 275 nanometers, and you can see the clear difference in inactivation curves that actually, 254 and 275 here, that actually we explain as a difference in a mechanism of inactivation for this wavelengths. So moving on, we also got very interesting results when we combine two wavelengths, 255 and 289 nanometers. And this combination produced a synergistic effect for E. coli and Listeria strains. And what synergistic effects means, it means that actually, lot count reduction achieved was significantly higher than predicted additive effects. So, and it actually says, and this result says that actually, we can improve the lethality of LED by combining different wavelengths, but and the main conclusion actually that we did, based on the results of this experiments using model solution, that yes, 255 nanometers is not the optimal wavelength. All tested food pathogens, they picked UV sensitivity at 255 or 268 nanometers. And certain wavelengths, they may reduce these instances of tailing or shouldering. And we can pick wavelengths based on the sensitivity of target organisms and alternate mechanism of inactivation in, in closer to UVB or UVA area, they exist. And also, we showed that synergistic effects are possible for certain wavelengths, but they will be different, for different types of organisms. So, and also, to continue with research, we decided we needed to find the wavelengths that will be optimal, for fresh produce itself. And we considered the irradiance of LEDs and their germicidal efficacy. And based on this, trade-off, we came up that, with the wavelengths of 277, that in our opinion was optimal for inactivation for the irradiance that we could get from this wavelengths and considering the cost. So, and actually, this part of our research was recently published in the Journal of Innovative Food Science and Emerging Technology. And for the attendees who are interested in this research, I recommend this article, that was published in 2019. So the next step in our research was to compare the efficiency of low pressure lamps and 277 nanometers UV LEDs for the fresh produce itself. So, and we used romaine lettuce and apples for this research. And also we wanted to see, okay, is there any, benefit of using LEDs on refrigerated temperature? That's very typical, in food production. So, and we also compared the germicidal efficacy of dry versus water-assisted treatment with low pressure lamp for produce disinfection. So here are the units that we used in the second part of our research. So 254 versus 277 nanometers, and we for at the lamp technology, we used the UV box, and we had lamps from at the top and at the bottom of this chamber. And for UV LEDs, we used custom-made unit from Agrifood. So, and here are, the samples that we used in our research, and the difference between romaine lettuce and apples were that, we inoculated apples with Listeria, and we inoculated romaine lettuce with E. coli or 1/7H7. So in here, the first results, we can see that 254 nanometers light was more effective against E. coli. And actually, this is logical. If we recall the germicidal, the action spectrum, or actually, of E. coli. So it has a maximum sensitivity to 59 nanometers. And if you look at the results, you can see that with direct exposure, lettuce to the UV light, the reduction that we've got was maximum 1.5 reduction, 1.5 logs, and the doses were quite high, 100 millijoules per centimeter versus 500 millijoules per centimeter square. And for the apple, in addition to pathogenic organisms, we also looked at the so-called blue rot organism, Penicillium expansum, that actually causes the spoilage of apples, and and the damaged fruit are particularly susceptible to this organism. And we wanted to see, okay, how UV will also affect the spoilage organism on the fruits. So the first test we did was 254 versus 274 against listeria on apples. And in this case, 277 nanometers light was more effective against listeria. And, we've got about like 1.5 log reduction at 1,000 millijoules per centimeter square. And this is quite high dose, compared to the doses that is used for water treatment. However, this dose, was lower than the dose at 254 nanometers. So in comparing the efficacy of 254 versus 277 for penicillium and for listeria, we can see that actually a log count reduction obtained for fungal spores was much higher than for bacteria. So, and actually, at 1,000 millijoules per centimeter square, we've got almost like 3 to 4 log reduction compared to 1.5 for Listeria monocytogenes. So actually, these results, they raised us, they raised a few questions about, the effect of the skin of some compounds that can present in the apple itself and have, kind of, protective effect. So, and also when we treated with 277 nanometers LEDs at 67 millijoules centimeter square, we can actually, we were able to inactivate all background microflora on the apple, and you can see the control versus treated apple on this slide. So, and this actually, this project actually continues, and we looked at the quality and shelf life of apples, after exposure to UV lamp and UV LEDs. And the results, right now, they are almost ready for publication. So I can share all the results here. So, and also it was interesting to see, as Keith mentioned, the effect of surface type on the efficacy of an activation of the, of pathogenic bacteria. As we all know, and Keith mentioned about shading effect of UV light, and actually this, it's kind of, limits the inactivation ability of this light. So, and if we compare apples, versus lettuce, so we can see that 254 was much more effective on lettuce compared to apple skin. So yeah, and we conducted some additional research to understand why it happens. So what we found actually that some bacterial cells, in this case is listeria, become lodged within the microscopic crevices, and here you can see electron microscope picture that actually that shows this, and it shades kind of bacteria from UV exposure. So and so in this case, I think removal of bacteria from the surface, could clearly increase the efficacy of UV light. So that's why we tried this water-assisted UV treatment, and earlier this application of this treatment was reported against novavirus on blueberries. So, and these are our dry and water-assisted UV treatment, the comparison. So in this, for water-assisted treatment, we submerge produce in water under constant agitation and exposed to UV light. So, and at the same time, microorganisms, are dislodged from the surface of the fresh produce. So this way we kind of, reducing the shading. However, the cross-contamination is a concern. So this is a setup, for our lab setup for water-assisted treatment. You can see the sample that is agitated by a magnetic stir bar and stir plate, and then we put this sample inside of the UV chamber. So, and here are the results. You can see that, yes, water-assisted UV treatment is much more effective than E. coli, for E. coli against on lettuce. So we've got 256 versus 142 log reduction. And, we measured the presence of E. coli in wash water on the skin, and you can see that after 5 exposure of the sample to 500 millijoules per centimeter, there was no organism detected in the wash water. So actually, this was very good result. And a similar result we got for treatment of listeria on apples. So water UV treatment was much more effective against listeria on apple skins. 1.73 versus 1.9 log reduction. And in wash water, the counts of listeria were lower than level of detections. So you can see the comparison of dry and wet treatment on this slide. So, and the last thing that we did, this research, we compared the performance of LEDs at 277 nanometers and 268 nanometers at cold temperature, because the cold storage at 4 degrees is very typical for food industry. And we what we found, the first thing that we found was that, okay, the irradiance of LEDs increased at the cold temperatures, and actually this allowed us to reduce the dose to receive the same log reduction, but we didn't see any increase in log reduction itself. However, I think this is clear the advantage of LEDs, the high performance at low temperatures. So in conclusion, I must say that the efficacy of 277 nanometers light against pathogen, of course, depends clearly on the produce type and the target pathogens. So it was less effective against E. coli on lettuce, but most effective against listeria on apples. So the positive side is UV LEDs showed increased better performance at lower temperatures, and they may be very effective for inhibition of growth or disinfection at refrigerated areas. And yes, water-assisted treatment can improve UV-mediated inactivation of foodborne pathogens. And yes, this research was done in lab scale, using the lab scale units. And of course, the next step is scaling this technology to commercial units. And however, there are certain hurdles because of the price, and we need to use to test it, in pilot plant or industrial production. So, and we are working at the second second publication on application of UV LEDs directly for fresh produce. So, and right now, yes, the price for LEDs is definitely a hurdle, and the research that also needs to be done is, testing different combination UV LEDs and multiple wavelengths for dry and for wet treatment. So, and this research actually, was done in my lab, and I would like to acknowledge, the contribution of, visitor from Brazil, Vanessa de Souza, and this is my staff who did this research and published the research in, in the papers that I presented. So this is what I had. Hello? Hello? Okay.
Thank you very much. So I'd like to thank Dr. Koutchma and Dr. Warriner for presenting today. And at this time, I invite all the attendees to, if you have a question that you'd like them to answer, to type it into the Q&A window there. And Keith and Tatiana, if you could, as the questions come in, if you could just verbally read the question and answer it.
Yes, I see the question. Tom Hamling, have you done any work looking at 222? Yes, actually, earlier, actually, we worked with eczema lamp, and this eczema lamps, they emitted light at 222 and 282. So, and we have research published actually, for 222 nanometers, and we look at treatment of juice and milk. And these two papers for 222 are published, but we did have LEDs at 222 nanometers. Next question, are the nutrients affected? Actually, yes, the doses are quite high, and actually we conducted the research looking at, at quality and nutrients, and the results are actually, very good. The nutrients were not very much affected. There was some reduction, but not very, not very high. So actually, they affected, but but not at such a high degree. So this is my answer. Have you considered the use of eczema technology for your research pipeline? Yes, like I said, we already used eczema technology in our research. We used eczema lamps at 222 and 282 nanometers, and these two papers actually, for juice and for juice and for apple juice and for milk, they are published. So yeah. Do you think there may be a dual chemical UV curable solution to target this need? UV curable solution to target this need. I'm not sure if I understand the question. Okay.
I think it might be asking about like a chemical disinfection plus the UV.
Yeah, I was just asking about how effective a medium pressure lamp. So the trouble with medium pressure, isn't it, Tatiana, that they just get too hot in order to use, unless you've got an application in water, isn't it? So
right.
yeah, medium pressure lamps. Yeah, more for water rather than. But going on to the pulse light, which is this sort of wide spectrum light, so that people have suggested that it's more effective than UVC I254. But with all UV systems, it's not the potency of the light. We know it can damage. It's the how do you direct it to the target. That's the key point.
I mentioned
just want to add does 5-log surface reduction? Oh, sorry. Oh, I thought you were going to talk about the 5-log reduction on the surface from a safe level. And yeah, the 5-log reduction, people debate a lot about it. Essentially, 5 logs means a assurance of 99.999% of the time you'll decrease the pathogen. So 5 logs is a target, but 2 or 3 logs is acceptable, and complete elimination can be important as well. Do you want to take the next one then, Tatiana?
Oh yeah, using chemicals and UV technology to cure perhaps like
you are.
Yeah, this is visibility definitely. And I think I think it's already done. Using UVA and coating. So and UVB. That some compounds in the coating. They can generate this reactive oxygen species. So then it works as a combination. So yeah. Yeah, it's possible. The key is to affect the DNA pathogen right. Like I said, I had a slide. There are like different mechanism of UVA and UVB and UVC, and only UVC, directly affected DNA. I think, the key is to find the most favorable combination, to combine, the DNA damage with other mechanisms. Then we have this synergistic effect. I think this is, the true advantage of LEDs. Okay, we can offer 22 nanometer sample lamps if you guys are interested in testing. Yeah.
Always interested.
It's not everything.
In anything new.
Yeah. We had this, like I said, you remember, we had this, and it, 222, yes, it has a high penetration depth, but in the same time, and high energy of photon, it penetrate, deeper. However, we found some strange effect on the quality of food, so we need to be very careful, because we are still dealing, with with the quality and nutrients and so on. We don't want this off flavors of created. So we need to consider this as well. Yeah. What do you think? Okay.
So I'll do one last call if anybody has any questions for Dr. Warriner or Dr. Koutchma. And just as we wait for that, just do one more reminder that the 2019 IUVA World Congress is coming up February 10th through 13th in Sydney, Australia. You can find out more at iuva.org. And the RadTech Big Ideas Conference is also March 19th through 20 in Redondo Beach, California. And you can find out more at the bigideasconference.com or radtech.org. I'd like to thank Dr. Keith Warriner and Dr. Tatiana Koutchma again for presenting on this. Oops, we have some more questions.
What about the virus? Yeah, the question, the last question. What about the virus? Keith, do you want to take this one?
Yeah, so with viruses, the big ones of concern at the moment is obviously norovirus and hepatitis, and that's to do with soft produce. So the thing with viruses, especially norovirus, they can be fairly tough to inactivate. I'm not sure what the dose is to get a 1 log reduction, but I think it's more than it is for a bacteria. So viruses, and the other one is parasites like Cryptocyclospora. And the thing in common is not only are they very highly UV resistant, but they're very difficult to study in that you can't culture them. So there are sort of surrogates that you can use, but it is an up-and-coming serious threat, and how the technologies can inactivate them are largely unknown. But we do know that you can inactivate them. It's just you have to deliver that dose at the right direction and right, obviously, intensity.
Yeah.
Where is the best served at commercial-wise? Oh, the LEDs. I don't know, Tatiana. Do you know commercialization? So do you know where the best LEDs are sold?
Like I showed the slide, for optimization, we worked with 277, nanometers. It was the wavelength that we used because it was, affordable. It had high enough irradiance, and it had high enough germicidal efficacy. So so irradiance, germicidal activity, and also the price, these are the main factors to consider, to build a commercial unit. As I said, yes, this is the next step, this needs to be tested in a commercial scale. So using, this LED packages, and modules, and they should be built over conveyors. So yeah, there are definitely, this is the next stage, next step, for this technology, to move further, for food applications. Yeah.
So another question asking about the shorter wavelengths are very low penetration, which is very true. They can't be used, but the longer wavelengths at 365. Now, there are certain treatments where you can get photoactive coatings, for example, that work with 365 in things like titanium dioxide, and there are sort of photoactive ones, but the actual antimicrobial properties of 365 are very low. because obviously they don't absorb onto the DNA. So they can be used, but they need to be used in combination with a photoinducer, as I call it, or photoactivator.
Yeah, I agree, completely agree. And yes,
well,
this is my point.
So yeah, I think the next question is for you, Tatiana, about commercial availability of LEDs.
I don't know, do you buying the units, you're not buying.
You do a good sales pitch. Well, I think as from my sort of experience, you pay for what you get. So if you see LEDs that aren't expensive, then you know why. So I think the ones coming out the US are very good. I think the ones coming overseas may not deliver as much, but I think the technology is really changing quickly, and through previous experiences with certain LEDs, it was bad, but technology advances and they do get cheaper. But certainly, buyer beware, I think, is the watchword.
Yeah, and actually, I'm learning more and more about LEDs, and I understand, how packaging, itself, how the efficacy of LEDs, all this, like, scale up steps that, that are done, in manufacturing LEDs are very important, so yeah, so like, so I think, my point is, I don't know the product that it's like, ready, to be used, for in the food market. So, but, I think this research, this first step, they can kind of, define this direction, what to do next, and how this should be done, in order not to fail this technology, because definitely, this technology has lots of potential, but it needs to be done properly, So, yeah. So in this collaboration between LED manufacturers, equipment manufacturers, researchers, and so yeah, we are learning, we are learning. It's a learning process.
Oh yes, always keep always learning. That's the big. What is a photoactivator? Well, photoactivators are agents that can be activated by UV light, which give the antimicrobial effects. So the most classic one is titanium dioxide. So we put titanium dioxide on the surface, and when it's illuminated by UV at 365, it generates these radicals which can inactivate pathogens. So they're being used as antimicrobial coatings. And there's other ones. There's other agents that are photoactive, make into a radical, and then go off to kill whatever that's touching them. So they're the photoactivators. There was some interest in photoactivation for coatings, not so much obviously on food, but that's the sort of underlying premise of those. What is the legal status of the wavelengths of? That's a very interesting question, and I think Tatiana knows more about the regulatory side, but certainly for a long time they were only allowed to use 254 nanometers to stop people using different wavelengths, because they knew all the knowledge of antimicrobial activity had been developed using these lamps, because that's all that was available. I don't know, Tatiana, do you know what the legal status of LEDs other than 254 is? I think it's still there, isn't it? I think you have to have a 254 if you're going to promote it as antimicrobial.
In Canada, it's definitely 254 nanometers. They're only low pressure lamps. They are actually, legalized. In US, yes, for juice treatment and for food surfaces treatment is also 254 nanometers. There is one application for treatment of water, pasteurization of water in dairy, in milk PMO, that allows using of medium pressure lamp and this polychromatic spectrum. And I think, there are other wavelengths that I approved for use in, to form vitamin D, or, in Europe. I'm not sure, but it may be, so. But the point is, yes, in order to use, this other wavelengths, yes, the regard, they should be approved, by regulators. Okay. Any other questions?
Yeah. Give it a second here, but it looks like we might have gotten all the questions.
Okay.
All right. Well, I would like to thank Dr. Warriner and Dr. Koutchma for sharing their knowledge on this. I'm glad somebody's working on this because one of the numbers that wasn't shown up there was me in spring of 2018 with that E. coli outbreak with the lettuce, I think. And I hope you guys work out all the bugs on this so that there's no more bugs in the food. But I'd like to thank you both. I'd like to thank the International Ultraviolet Association and RadTech for doing this too.
Okay. Thank you.
Thank you all. Have a great afternoon.
Thank you.